Good morning, students. Myself, Vijay Shankar from ECE Department, Civil Engineering College. Today, we are going to discuss about another topics in the electrostatics. Yesterday, we completed the electric field intensity due to infinite line charge. Now, today, we are going to discuss about the electric field intensity due to circular ring. Electrical field intensity due to circular ring. So the electric field due to the charged circular ring. The charge is fully distributed, uniformly distributed on the circular ring, and on that we assume a small differential length, on the DL here, a small differential length DL on the circle, and that circle is uniformly distributed with all the charges, and that charge, uniformly distributed charge, we can consider as a Royal charge density, and then a small differential charge dq is equal to Royal into dl. We know this one, the Royal into dl. At the rate of change of the charge with respect to the length is the charge density. Got it, my dear students? Now see, consider a charged circular ring of radius r placed on xy plane with center at origin, carrying a charge uniformly along its circumference. The charge density is Royal. The point P is at a perpendicular distance z from the ring. Okay, see here, for the circular ring, there is a perpendicular line, the distance of z, a point on the z axis P, and you can join a small differential length and the P towards the upward direction. Okay, upward direction only. Consider a small differential length dl on this ring. The charge is on it is a d. dq is equal to Royal into dl. We know the differential electric field intensity, the Royal dl by 4 pi epsilon naught r square into ar bar, where capital R is the distance of point P from the dl. You see the distance of point P from dl, to the point P. Now consider the cylindrical coordinate system for DL. We are moving in phi direction. Where DL is equal to R into d phi. Why it is means in the cylindrical coordinate system? Suppose the cylindrical coordinate system is like this: a plane with move of phi angle, including with the r radius. Okay, one of the differential element in the cylindrical coordinate system that we consider as a DL is equal to R into d phi. So actually the R, phi, and Z is a coordinates in the cylindrical coordinate system. dr is a differential element, and R into d phi is another differential element, and the dz. Okay, this R into d phi with radius r of the circular, dl is equal to R into d phi. Got it, my dear students? Now, what is the R square here? R square means R square plus Z square. Why? The hypotenuse is equal to side square plus side square. So R square is equal to small r square plus Z square. See here, it looks like a right angle triangle. The distance of R here and with the distance of Z, and the hypotenuse is a capital R. So capital R square is equal to small r square plus Z square. Got it? Then, see, while the R bar can be obtained from its two components, the cylindrical system, the distance R in its direction. See, the direction is towards the, see, the diagram look like this. The R bar, we need R bar. The direction of AR bar is in the negative direction, AR bar minus, and here the point P is there, point P, and the direction is towards the positive direction of AZ bar, AZ bar. Okay. Now, to find this R bar is equal to find the R bar, and these two are meeting at the point P, with the distance of small r here and the distance of Z. So combining the equations, R bar is equal to, combining these equations, R bar is equal to Z into AZ bar, Z into AZ bar minus, because it's a minus means it goes in the negative direction of R. The positive direction of R is towards the downwards, and upwards is the negative direction of the R. So R into AR bar, R into AR bar, capital R is equal. So you got this one, minus R into AR bar plus Z into AZ bar. And its magnitude is, what is the magnitude of R bar is equal to, R bar is equal to under root of Z square plus R square, Z square plus R square. Now to find the unit vector, what is the unit vector? AR bar is equal to, AR bar is equal to R bar by the magnitude of R bar. We know this is a formula, the vector form and the magnitude. What is the R bar? Z AZ bar minus R into AR bar whole divided by, and its magnitude under root of Z square plus R square. Got it, my dear students? Z square plus R square. Then all these values you can substitute in the DE bar. You know the DE bar is equal to, DE bar is equal to DQ. DQ is nothing but rho L into DL. The rho L DL, the rho L DL by 4 pi epsilon naught, 4 pi epsilon naught. And this function is R square is there. Okay, R square into AR bar. This is a formula actually. AR bar. What is the R? R bar is equal to minus R into AR bar plus Z into AZ bar. Don't substitute this one. This is only the R function vector form. You have to substitute the magnitude of R bar under root of R square plus Z square whole square. And AR bar we got as this total function and substitute here. Okay. Then so see here, we got DL bar is R into D phi. Previously we've seen is a small differential length on the ring, and it is tilted with the phi direction. That is a differential element is a D phi with R. So rho L into R into D phi pi 4 pi epsilon naught R square plus Z square. Here it is R square plus Z square is there, and here it is under root of R square plus Z square. Totally R square plus Z square whole power 3 by 2. Got it, my dear students? And it is multiplied with the minus R into R bar plus Z into AZ bar. In yesterday class, I told that if any equilibrium condition is there, an equilibrium condition, when In the z-axis, a small differential element on the positive real axis means there is the same thing in the negative real axis also. There is no any component of z. There is no any component of z in the electric field intensity due to the infinite line charge. Okay, we are eliminating the z component there. Similarly, here also, a circular ring having a small differential length on this, and here it is in the positive direction, and there is another differential element dl is also you can consider. Both it is a get cancel at the equilibrium condition. See, the radial component of p bar at point P will be symmetrically placed in the plane parallel to the xy plane and are going to cancel each other. Hence, neglecting the AR component from DE bar. We are neglecting the AR bar component. Previously, we neglected the Z bar component. Why it is a Z component we are cancel means the charge is uniformly distributed on the Z axis. We are taking the line that is on the Z axis, and here we are taking the line on the circular ring. Okay, on the circular ring we are taking. See the circular ring radially components. So the R bar component is eliminated or neglecting in the DE bar. So after that, the R bar is neglecting. So there is no any R bar function. So finally, the rho L R into D phi by 4 pi epsilon naught R square plus Z square whole power 3 by 2. After eliminating, we have only the one component, that is the Z component, Z into AZ bar. Okay. And see here the differential element is a d phi, and in the right hand side the differential element is a d bar. So apply the integral on both sides. E bar is equal to integral rho L R d phi by 4 pi epsilon naught R square plus Z square whole power 3 by 2 Z into AZ bar. And that is equal to, why I am taking the 0 to 2 pi means we know the R, phi and Z having the variables. R is varies from 0 to infinite, and phi is varies from 0 to 2 pi, and Z is varies from minus infinite to infinite. You know, these are variables we have. So here the differential element is a d phi. So you are taking the integral term is phi values 0 to 2 pi. So the remaining all components is a constant rho L R 4 pi epsilon naught R square plus Z square whole power 3 by 2 Z into AZ bar. So integral phi into d phi. There is no phi, sorry. Integral d phi only is from 0 to 2 pi. So integral d phi is a phi with upper limit is 2 pi and lower limit is 0. Got it, my students? The lower limit is 0. So upper limit 2 pi only will get. So take it as a 2 pi and it is a cancel with the 4 pi here, remaining only the 2. Therefore, E bar is equal to rho L R, and here is a Z is there, and whole divided by, after cancelling of 2 pi here, we have only the 2 into epsilon naught R square plus Z square whole power 3 by 2 into along the Z axis, AZ bar, where R is the radius of the ring. Okay. So Z is a perpendicular distance of point P from the ring along the axis of the ring. This is the electric field at a point P 0, 0, Z due to circular ring of radius R placed in the XY plane. Got it? That is the second application. You see the next one is the gas law. The gas law is in fact alternately statement of the Coulomb's law. The gas law can be used to find E bar R, D bar for symmetrically charged distribution, such as point charge, an infinite line charge, an infinite sheet of charge, and a spherical distribution of the charge. Okay. The gas law is also used to find the charge enclosed charge enclosed or flux passing through the closed surface. Flux passing through the closed surface. The gas law is also used to find the charge enclosed through a closed surface or flux passing through the closed surface. See, considered a closed surface and keep the inside there is a positive charge. From the positive charge, there is a magnetic lines of force terminating radially from that. Inside the whatever the charge is at the closed surface radially, and these magnetic lines are not crosses each other and never crosses each other here, and these lines possess a small differential surface or the unit surface area. Consider the total number of flux lines leaving from the surface is equal to the charge enclosed inside the closed surface. Okay, both are equal. So magnetic flux psi is equal to the whatever the charge is there inside is equal, psi is equal to Q. Okay. The same thing, gas law is also used to find the charge enclosed or the flux passing through the closed surface. Flux is a psi and charge is a Q. Note that whether the charge distribution is symmetrically or not, the gas law holds for any closed surface, but can be easily applied for the symmetrical distributions. But gas law cannot be used for to find E bar and D bar if the charge distribution is not symmetrical. So the gas law is not applicable for whenever it is an unsymmetric value, not a symmetric, non-symmetric functions. Okay. Then let us see for the point charge of the electric flux. So the point charge for the gas law. You know the gas law is equal to so this x-axis, y-axis, and the z-axis. A plane we already have is a plane. That plane is moved towards the right direction, is the phi direction, and with a radius of r here. That radius is, you can consider as an A, and the theta is also there. So we can consider this a spherical coordinate system. Spherical coordinate system. Having the phi, having the radius r and the theta, it is a spherical coordinate system. Consider the differential surface area ds, a small differential surface area at the point P. The direction normal to the surface ds is a AR bar. The normal to the direction is a AR bar because the line is R here and that AR bar only the direction. Consider a spherical coordinate system. The radius of sphere is A. The radius of sphere is A. And the direction of d bar along AR bar, which is normal to the ds at any point P. In spherical coordinate system, the differential surface area normal to AR bar direction. Here, remember, my dear students, in a spherical coordinate system, what are the differential elements in the spherical coordinate system? Actually, the coordinates are r, theta, and phi. These are the three coordinate system we have in the spherical coordinate system. Differential elements are dr, and for theta, r into d theta, and for phi, r sine theta d phi. These are the differential elements we have. You know this one. And in a spherical coordinate system, the ds normal to the radial direction of AR bar. Normal to the radial direction of the AR bar. Okay. Why I am saying it is a normal to the radial direction of AR bar means consider a closed surface. Inside there is a charge is there, and a magnetic lines of forces terminating for the positive charge radially, circularly here it is, and it is passes a differential surface area on the closed surface. It is in the along AR bar direction. So whenever there is a differential surface area, ds r bar is equal to means r bar is equal to AR bar direction. Whenever there is an R bar direction, means there is no any component of dr. Only the remaining components we have, that is r d theta, r sin theta, d phi. R d theta and r sin theta, d phi. Because it is in the along AR bar direction. What is R into R? It is R square sin theta, d theta, and d phi. And we consider here the R is equal to E. R is equal to A. So A square sin theta, d theta, d phi, as of R is equal to E. So ds bar is equal to. See, if there is any ds and the ds is equal to same, when I am considering this a ds bar and it is a magnitude, in general direction is a an bar. It is a formula actually. ds bar is equal to ds into an bar. Without the vector form, it is a scalar. ds is equal to ds only. Whenever it is a vector, means having the magnitude and also the direction. The direction is a an bar direction. Okay, ds into an bar. What is the ds we have? R square is nothing but now it is a square sin theta, d theta, d phi, and we are taking along the an. An is nothing but here the AR bar direction. Okay, AR bar direction only. So ds bar is equal to a square sin theta, d theta, d phi, AR bar. Got it, my dear students? Now, according to the point charge of electric field intensity, what is the formula here? The Q by 4 pi epsilon naught R square into AR bar is a point charge of electric field intensity. And the point charge of the D bar means electric flux density. Electric flux density and electric field intensity relation is epsilon into E bar. In the free space, epsilon is epsilon naught only. Epsilon r is equal to 1. So you can substitute here epsilon into E bar Q by 4 pi epsilon naught R square into AR bar. Okay, and this epsilon is nothing but epsilon naught and epsilon r only. In a free space, the value is 1 here. The value is equal to 1. We have only the epsilon. So both the epsilon naught is get cancelled. D bar is equal to Q by 4 pi epsilon naught, not the epsilon naught here, 4 pi R square into AR bar. This is the formula you get in the point charge of the electric flux density. See here, the D bar is equal to 4 pi R square into AR bar. What is the R here? A square only. So Q by 4 pi A square into AR bar as of R is equal to E. Got it, my dear students? Then now we can apply the dot product of D bar and the DS bar. Dot product, in the signals and system also we've seen that it is the vector, orthogonality vector, D bar dot DS bar is equal to magnitude of D, magnitude of DS and cos theta. If it is a cross product, means magnitude of D, magnitude of S and sin theta. Okay. So now substitute the D bar is equal to Q by 4 pi A square into AR bar, and DS is A square sin theta, D theta, D phi, AR bar. Okay. Now I'm taking the magnitude here. Magnitude is Q by 4 pi A square only, and here the magnitude of DS is A square sin theta, D theta, D phi. Okay. And these two magnitudes and the theta is equal to 0 degrees. Theta is equal to 0 degrees. Now the D bar dot DS bar is equal to substituting of Q by 4 pi A square into, and this is a function up to this function is a D bar. and the ds bar is a square sine theta d theta d phi is a ds bar. And here the formula itself, the dot product, the cos theta is there, cos 0 degrees. Cos 0 degrees. So d bar dot ds bar is equal to q by 4 pi. And here the a square get cancelled, sine theta d phi, and cos 0 is a 1. So d bar dot ds bar is equal to q by 4 pi sine theta d phi. Got it, my dear students? So alternately, to avoid the confusion between the symbol of theta, we can write it as d bar dot ds bar is equal to q by 4 pi a square ar bar dot a square sine theta d phi ar bar. Without knowing that is a magnitude of ds and cos theta, and why the cos theta value is again it is a 0 like that. Without knowing this, directly you can substitute d bar and ds bar in this function. So we know that ar bar dot ar bar is equal to 1. Dot product itself is a 1. Okay, ds bar dot ds bar is equal to q by 4 pi sine theta d phi. And according to the Gauss law is saying that q is equal to integral d bar dot ds bar. Integral d bar dot ds bar. Q is equal to, or nothing but it is a psi is equal to, actually the psi is equal to, the psi and q is both are same. Now we are proving that the Gauss law of Coulomb's law of flux crosses the surface if q coulombs of charge is enclosure of that surface. So psi is equal to d bar dot ds bar. Substitute the q by 4 pi sine theta d phi. See here the integral is applying for the with respect to the theta and the phi. What is the theta is varies from the 0 to pi, and phi is varies from the 0 to 2 pi. We know theta is nothing but the cone. It is extended up to the 0 to rotated with the 0 to 180 degrees only. So q by 4 pi is a constant. The sine theta integral is minus cos theta, and integral d phi is a phi. Okay, substitute the upper limit and lower limits. Cos theta, cos pi minus cos 0. Cos pi is a minus 1. Cos 0 is a 1. Okay, and why it is a minus is internally means there is a minus sign here. See the minus I am keeping in the outside. Cos theta, and it is a pi and the 0. So minus of cos pi minus cos 0. Okay, minus of cos pi minus 1, and it is a cos 0 minus 1. So minus 1 is a minus 2, and it becomes a 2. Got it, participants? And integral phi d phi is there, phi 2 pi and 2 pi, and the 2 pi will get as a upper limit. So totally 2 into 2, 4 pi get cancelled, and psi is equal to 0. So finally we are saying that this proves the Gauss law that q coulombs of flux crosses the surface. Q coulombs of flux crosses the surface if q coulombs of the charge is enclosed by that surface. Means the plus is there inside the closed surface. The flux lines outside is a psi is equal to inside the charge. The flux lines leaving from the surface is equal to the flux lines psi leaving the surfaces outside is equal to the charge enclosed inside. So psi is equal to q. Got it? This is a very important. We have to prove the psi and q both are the same. Flux, magnetic flux psi is equal to charge. Now use of Gauss law to obtain d bar and e bar. Now we are using the instead of psi it is a q. Q is equal to integral d bar dot ds bar. Q is equal to integral d bar dot ds bar. Okay. For a sphere of radius r, the flux density dr in a radial direction ar bar always let d bar is equal to dr. Let d bar is equal to dr. So for the sphere of radius r, the flux density d bar is radially the direction ar bar always let d bar is equal to dr. Means d is equal to d. Let us take d is equal to d only. When the d bar is there, this changes as a vector. So having the direction is ar bar. So take the component. dr is a component. So d bar is equal to dr into ar bar. Let the Gaussian surface of the sphere of radius r enclosing the charge q. You see, the Gaussian surface ds bar is equal to the spherical coordinate system. This differential surface area normal to the r bar direction is r square sine theta d theta d phi. Now only we've seen that. And ds bar, d bar is we now assuming the dr into ar bar, dr into ar bar, and ds is r square sine theta d theta d phi into ar bar. So ar bar dot ar bar is equal to 1. The remaining functions, the d bar magnitude is a dr and ds magnitude is r square sine theta d theta d phi. Okay, ar bar dot ar bar is equal to 1. Now take the integral on both sides, integral d bar dot ds bar, and here also integral with respect to the theta and with respect to the phi. Okay. Now the same way the previously what we did in the cos theta with the substituting the pi and 0 and phi with the substituting the 2 and pi, we'll get the here the 2 and here the 2 pi. So total it is a 4 pi. Okay, 4 pi r square into dr. But d bar dot ds bar according to the Gauss law, the value is a q. So q is equal to 4 pi r square into dr. What is a dr now? Dr is equal to q by 4 pi r square. Okay, substitute that in the d bar component. D bar is equal to having the magnitude is dr and the direction is ar bar. What is a dr component? We got a q by 4 pi r square and the ar bar. Okay, by using the Gauss law, we derive the electric flux density d bar of the point charge. Similarly, the E bar is equal to, what is the E bar is equal to? D by epsilon naught, or D is equal to epsilon naught into E bar. Okay, this is a relation. And E bar is equal to, what is the D bar? We got a Q by 4 pi r square into epsilon naught AR bar. So now we derive the point charge of electric field electric flux density and electric field intensity by using Gauss law. Or Gauss law is D bar dot ds bar is equal to Q. What it matters, students?